Worker threads help us offload CPU-intensive tasks away from the event loop so that they can be executed parallelly in a non-blocking manner. Although, they do not help us much with I/O or input-output intensive work, since the Node.js built-in asynchronous I/O operations are much more efficient themselves. Each worker thread has its own isolated V8 environment, context, event loop, event queue, etc. However, they can share memory. They can do so by transferring array buffer instances or sharing shared array buffer instances with one another. Also, a worker and parent can communicate with each other through a messaging channel. Note that in Node.js, it's important to differentiate between CPU-intensive, long-running event loop blocking operations and I/O or input-output operations, such as HTTP requests and querying the database, etc. For us to better understand when worker threads might come in handy, let's switch over to our IDEs and generate a new Fibonacci module. Inside this module, let's also generate a new Fibonacci controller that we'll use to test out a few ideas. Let's open up this newly generated controller file and declare a new get route there as follows. This endpoint will accept one query parameter, n, which is the nth Fibonacci number. Inside this method, let's implement the Fibonacci formula. Note that there are no I/O operations here, so this is a perfect example of a CPU-intensive, time-consuming and/or blocking operation. Let's save our changes, open up our terminals, and run our application in development mode with npm run start:dev. Once our app is bootstrapped, let's open up a separate terminal window and use curl to call our get Fibonacci endpoint, passing $n with our query parameter equaling 41, where 41 represents the 41st Fibonacci number. Below the video, you'll find the curl code so you can copy-paste it and try it out for yourself. As we can see, it took approximately 5 seconds, which may not seem like a long time, but since calculating the Fibonacci number is a synchronous blocking operation, during these 5 seconds, even if someone tried reaching our API, our application would not be able to respond. That means if there were any other HTTP requests during this 5-second time frame, all of these would have to wait until this specific Fibonacci calculation is done. As you may have already guessed, this is far from ideal. So, case in point, situations like this are exactly when worker threads might come in handy. Instead of blocking the main thread, we could delegate that operation to a separate worker, therefore our API would remain fully responsive and operate like normal. Let's start by creating a worker file and naming it fibonacci.worker.ts. Inside of this file, let's paste our Fibonacci function. Next, we need to register an event listener, listening to incoming messages from the parent port, our worker's parent. To do so, let's utilize the parent port object imported from the worker_threads module and register the onMessageListener. As an input argument for the callback function, let's use nID destructuring the incoming message object, where n represents the nth Fibonacci number to be calculated, and ID is the unique request call identifier. And last but not least, inside this callback function, let's calculate the Fibonacci number and respond to the parent port using the postMessage method, passing the unique call ID and the result. Let's save our changes, and next to the Fibonacci worker file, let's create another file and name it fibonacciworker.host file. Inside this file, let's declare the injectable Fibonacci worker host class that implements two lifecycle hooks, onApplication Bootstrap and onApplication Shutdown, as well as provide a run method where we'll set up the logic that helps us communicate with the underlying worker. Let's also declare two private properties in this class, worker, which represents the underlying worker instance, and message $, which is where we'll store our messages in an RxJS observable stream. More on that in a moment. To start things off, inside of our onApplication Bootstrap method, let's initialize the worker instance. Let's create the message $, event stream using the fromEventHelper function from the RxJS package, constructing a stream based off the this.worker onMessage. With our Bootstrap phase all set up, let's move on to the onApplication Shutdown method and make sure we clean everything up. Here we just want to terminate the spawned worker, so let's call the terminate method on it. Now, let's move on to the fun part and set up the logic itself. Inside of our run method, let's first generate a unique ID. We will use this ID to differentiate requests, as each message will have its own unique ID, so that we can associate it with a given specific request. Next, let's send a message to the worker using the postMessage method, passing in an object that consists of two properties, n and ID. Note that we could have used ArrayBuffer and SharedArrayBuffer to implement memory transfer, as we mentioned at the start of this lesson, or share between threads to make the execution even more efficient. Lastly, let's return the value from our messages observable, making sure to filter it based on the unique ID and grabbing the result value. If you're not too familiar with RxJS, it's unfortunately out of the scope of this course to dive into all of the specifics, but just know that here we're essentially piping the stream, filtering by unique ID, and then mapping and plucking that result value, just as we mentioned. If you're interested in learning more about RxJS itself, check out the official documentation at rxjs.dev. Great. Let's save our changes and navigate to the Fibonacci module to register our Fibonacci worker host as a provider there. With our provider registered, let's switch to the Fibonacci controller and inject our Fibonacci worker host there using the standard approach. And finally, let's replace our current Fibonacci method implementation with the following code that calls the run method of our Fibonacci worker's host. Excellent. Let's once again save our changes, open up our terminals, and call that Fibonacci endpoint once again. It works, perfect. Now for fun, let's change the n parameter to, let's say, 60, just so it takes a very long time to calculate that number, and call that endpoint again. In the meantime, let's open up another terminal window and see if our API is responsive by hitting another random endpoint. And as we can see, our API is still responsive now. Great. Next, let's try to hit the Fibonacci endpoint, but let's change the n parameter to something that shouldn't take too long, for example, 5. And as we can see, the application is hanging on us, but why? What happened? Well, the reason our application is hanging here is because our worker is still busy with the previous request that we executed, where we asked it to calculate the 60th Fibonacci number. But how can we overcome this kind of an issue? Well, to address this limitation, we could implement a pool of workers, so basically instead of having one worker instance, we'd maintain a pool, aka a collection of workers. Then, instead of delegating work to a busy worker, we'd just retrieve one that is available and free. In this lesson, instead of implementing static and dynamic worker pools by hand ourselves, we'll be utilizing the Pacina library, which will make things much easier for us and with a lot less boilerplate code. Pacina is a widely used node worker pool package that supports flexible pool sizes, provides fast communication between threads, and covers both fixed task and variable task scenarios. So let's get it installed. Once the installation is complete, before we continue, let's open up our tsconfig file and set the ESModule interop property to true, as it is required by this library. Next, let's move on to the Fibonacci controller and replace the classes constructor with the following code, initializing the Pacina worker pool and passing in the file path to our worker. Also, let's make sure to not forget to update the Fibonacci method to use the Fibonacci worker now as well. And last but not least, let's open up our Fibonacci.worker file and replace our onMessage event listener with a simple export. And that's it. If we save our changes, open up our terminals and use curl to again calculate that 60th Fibonacci number, and we switch to another terminal window and call the Fibonacci endpoint again with a different value of n, let's say 5. As we can see, we're able to start up multiple workers now without causing the application to hang, all while keeping our application fully responsive. So if you want, try to hit a random endpoint again and see if that works. With everything we've learned and done in this lesson, we can now handle any intensive tasks we need in our Nest.js application's future.